Hi, Algebra 1. Here we are looking at section 2.7, the last section of chapter 2. We're going to talk about square roots and real numbers. So our vocabulary brings us to the concept of square root, and a square root is basically a relationship between a number like 64 and the fact that 64 is equal to 8 squared, or 64 is equal to, or I should say, and 64 is equal to negative 8 quantity squared. So if I were to talk about the square root of 64, I can talk about the square root of 64 being positive 8 or negative 8. So the square root of 64 is the number that I would multiply by itself twice in order to get 64. A perfect square refers to numbers that have whole square roots, whole numbers as square roots. So for instance, perfect squares would be 1, 9, 4, that was out of order, my bad. 16, as we will see later on, we'll see these numbers all the time. 25, and I hope you're seeing 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, and we've got 36 and 49 and 64, and we can go on. I would honestly ask that you make an attempt to memorize your perfect squares up to, here's 121, I would say up to probably 15 or 16. I think 16 would do. This is the square root of 14. This is the square of 14 squares, sorry. And this is a perfect square. And this is the square root, I'm saying the wrong thing, the square of 15 and the square of 16. I think these are nice, easy, and memorable, and they will help you out in solving problems, guaranteed. All right, so that's perfect squares. The radical sign is the symbol we use to represent the action of taking the square root of something. So I might take the square root of 100 and I get 10, or I could take the square root of 121 and I get 11, or the square root of 64 over here and I get 8. If you notice, every time I'm writing this down, I'm writing down what we'll call the principal square root. The principal square root is the positive version of the square root of each of these numbers. So the positive 10 is the principal square root of 100. Positive 11 is the principal square root, even though 10 times 10 is 100 and negative 10 times negative 10 is 100. When I'm talking about principal square root, I'm talking about the positive root of that number. Irrational numbers. We talked a little bit about rational numbers before. Rational numbers back in the day, a few chapters back, were numbers that can be written as a fraction. Irrational numbers cannot be written as a fraction. Let me use my yellow here. Irrational numbers cannot be written as a fraction. And in this case, we're talking about writing numbers as a ratio of integers, right? So irrational numbers can't be written in that way. And also, when you think about the decimal version of an irrational number, they neither repeat nor terminate. They don't repeat or terminate at all. So an irrational number would be a number that goes on forever and ever without seeing any kind of nice little repetitious kind of a pattern, and it goes on forever and ever. So what do they look like? So for us, they're going to look like the square root of 2, the square root of 7, the square root of 9. Nope, just kidding about the 9. The square root of 19. Notice anytime I'm taking the square root of a number that's not a perfect square, I am going to have an irrational number. So all of these numbers they cannot be written as a fraction, as a ratio of integers, nor will they repeat or terminate in their decimal form. And now we're talking about real numbers. We remember real numbers are numbers that we can, in a sense, place on the number line. So even though these numbers, like let's say I was going to talk about the square root of 2. Square root of 2 is like 1.414, and it goes on and on. I can kind of gather where this number would be on a number line. And so 1 is here, and 1.414 would be slightly to the left of 1.5, and so I could approximate the location of it and say, well, the square root of 2 is about here. And so rational approximations are sometimes the thing that I need to do in order to get an idea of what the square root of a value would be. So this last idea of rational approximations really comes down to thinking about what the value would be. So let's take this guy for instance, the square root of 19. I know that the square root of 16 is equal to 4, and the next number up, the square root of 25, or the next perfect square, would be 5. So I therefore can assume that the square root of 19 is going to be somewhere between 4 and 5, and probably closer to 4, just given the location of 19 in reference to 16 and 25. So I might approximate this. I'm going to probably use a calculator, but I'd approximate this to be like 4.3 or something like that. And when I check the answer, I went and asked Mr. Google, I typed in square root of 19 and I got 4.35 blah, 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 which is a better approximation than I got, but still an approximation because we know that this is an irrational number that will continue on forever and ever. Let's get to some examples. So in this example, we are to find each square root, and as I look at this negative is not going to affect what I'm doing in here. The answer is going to be a negative, and let's see, what's the square root of 49? Hopefully you can see that the square root of 49 is 7, so I have a 7 in the numerator, and if you did as I asked you and memorized all of the square roots up to, all of the perfect squares rather, up to 16 squared, you would realize that this is actually 16, and so we get negative 7/16, and that's not reducible, so stick a fork in us, we're done, that's my answer. Over here, we're looking at the square root, plus or minus the square root of 0.81. And so my answer will also be plus or minus, because that plus or minus is not underneath the radical, so I'm cool with just leaving it out there, plus or minus 0.9 or 0.9. And so that's it. I mean, that's not too bad, right? All right, because I know 0.9 times 0.9 gives me 0.81, and 7 times 7 gives me 49. 16 times 16 gives me 256. You with me? All right, let's try another example. So over here, we're going to talk about, this is a concept summary, so not quite an example, but this is kind of a nice graphic, so I wanted to include it. Real numbers are the large number of numbers that we've been talking about. We've dealt with them, and we spent some time earlier breaking down rational numbers into integers, whole numbers, natural numbers, right? And then we had this other category of irrational numbers, and this is the category that we're going to be dealing with when we're dealing with square roots sometimes. And so here's what the breakdown looks like, or the layout. All right, so taking a look at this example, we're going to actually be classifying numbers. So name the set or sets of numbers to which each real number belongs, and we'll be referring back and forth to the graphic that we just saw. So 5/22, clearly I can write this as a ratio of two integers, so I know that 1, this is a real number, right? And 2, that it is a rational number, because rational numbers can be written as a ratio, right? Rational numbers can be written as a ratio of integers. Now, it's not an integer, and it's not a whole number, and it's not a natural number, so I'm going to stop there. Here I've got the square root of 121, which if you did as I asked and memorized your perfect squares, or your perfect squares, you would realize that this is 11, and certainly 11 is a real number, it's a rational number, it's also an integer, and it's also a whole number, and it's also a natural number. So it fits all of the categories that we saw over here on the left. Let's go ahead and take a look. Square root of 56. Now this does not resolve nicely. The answer is going to be some approximation of like, well, I know that the square root of 49 is 7 and the square root of 64 is 8. So it's got to be somewhere between 7 and 8, and so it's going to be approximately 7 point, I don't know, maybe 3 or something like that, or 7.2. And so the question is, does this number represent any number in our category? And yes, it is a real number, but remember what I told you before, when you have a square root that doesn't resolve, when you're not dealing with a perfect square, it is definitely going to be an irrational number. and so it's irrational. And over here we've got negative 36 over 4, which can be reduced into as negative 9. This number is clearly real. It is clearly rational. It is indeed an integer. But I don't know if you remember, would you call it whole or natural? Whole numbers start with 0 and continue up, and natural numbers start with 1 and continue up. So it is neither whole nor natural, but it is an integer. All right. If we take a look, we're going to graph each solution set. So we're graphing real numbers on a number line. So here, as I look at this number, I notice I'm going to read this as x is greater than, or x greater than negative 2. So we're dealing with all the numbers that are greater than negative 2. So I'm just going to put some values here just to give me an idea of what I'm dealing with, right? And so numbers greater than negative 2 do not include negative 2. So negative 2 is important, but I'm going to put an open circle there, because it is not part of my answer, but everything bigger than that, greater than that, will be a part of my answer. So I'm going to shade everything to the right, because x is greater than negative 2. And I have this answer there. And so the next value, the next one, has not greater than, but less than or equal to, less than or equal to. So again, I can put some numbers here. Sometimes I'm kind of lazy. I just say there's 0, and here's this number that I'm dealing with. It's after 0, and I'm going to do that here. 4.5 is a part of my solution. So A could be 4.5 or less than. So if A is 4.5, I'm going to put since I have the equal to, I'm going to put that 4.5 there, fill it in, and I'm going to shade everywhere to the left, because we see that A is less than or equal to 4.5. And here, with example 4, we're going to be replacing these symbols, using these symbols, replacing the circle with one of these symbols to make each statement true. And we just so happen to have dealt with the square root of 19, and we got that the square root of 19 was something like 4 point something. Do you remember how we did it? It wasn't too long ago. We know that the square root of 16 is 4, and the square root of 25 is 5. Therefore, the square root of 19 has to be somewhere between 4 and 5. Clearly, we recognize just from that information that the square root of 19 has to be greater than 3.888 repeating. Over here, we get 7.222 repeating, and this might be a little bit more challenging, but let's see what we can do. We see that the square root of 52 is going to be somewhere between the square root of 49 and the square root of 64. Square root of 49 being 7 and the square root of 64 being 8. This is not enough information to conclusively give me my answer, so I am going to employ a calculator of some sort. One of my favorite calculators to use is Desmos, which is an online graphing calculator. Totally a great place to have fun. And I'm not just saying that because I'm a little nerdy. So the square root of 52 is going to be 7.2. 11110 blah blah blah. Let's go back to our problem and see if we can take that information to help us solve it. So we had something like 7.2 with some ones going after it. Clearly, if these are 2's continuing after this 7, we can see that this one is greater. So I'm going to replace it with the greater than symbol. And the final thing that we have to do, I think this is our final example. The final thing that I think nope, not our final example, our almost final example is that we're going to organize these guys, organize these real numbers from least to greatest. And so the smallest is going to be a negative answer. And so we see that we've got 2 positive values here and here. So it's either going to be negative, the square root of negative 7, or 53 over negative 2. So with a calculator or with some ingenuity, you can get that these are the values of these numbers. Let me go ahead and draw little lines here. Let's use a little color. And then so here are the equivalent decimal versions of the answers. And this is going to be easy. Now that I can see this, I can totally number or change the order, or write from least to greatest, and it'll look like this. And this would be the way I'd order that. I think that this is enough for us today, and I think you have enough information with this problem to go ahead and start the assignment. So I'm not going to burden you with the sixth example. I'm going to let you go. Let me know if you have any difficulties. Recognize that this is the last section of not a super long chapter, but a long enough, and it's got enough information. It's pretty meaty. Let me know when you're ready for your test. I'll send it to you. Take care and